Okay, today's lecture is brought to you by Rice-A-Roni. Okay. Yes, yeah, there you go. Folks, did we take that quiz then? We took that pop quiz? Good. Settings. All right. All right, so what I'd like you to do now is, well, we can go over that quiz if we want. Let's see, results, view stats. Five questions. It was just 5 questions. It was out of 2.5 points, I think. All right. Folks, here we go. So, quick. Again, remember that these questions were all straight out of your notes. Nothing fancy. Nothing fancy at all. Okay? The first question, we got 100%. Good job. You guys all know that electrons in the highest energy level are valence electrons. They're not blanket electrons, which I thought was a fun answer. How many valence electrons does sulfur have?
Anything.
So you may take it, this is 6.
What?
We got anything. Yeah, we got NS.
What do you mean anything?
Like I got NA. We got
We got
You
what?
out cheap.
NA.
And then get a grade after.
It just says nothing else.
Well, I don't know. We'll have to figure out what happened. All right. Sulfur, 1, 2. If you look at that number, it's 1, 2, 3 positives and then 1, 2, 3 negatives. Sulfur's at the 2, right? Sulfur is going to gain 2 electrons. It's going to be 2 negative. Good. Question 3. That is the octet rule, which I told you would be on every quiz, right? If a neutral atom loses electrons, its charge, it's losing electrons, right? It's losing negative things. It's going to be positive charge.
You get one wrong. That's 2 out of 2.
The 2 out of 2. So, a neutral atom loses electrons, its charge is going to be positive. Because it's losing electrons. Then it's going to have more protons than electrons in the atom. And then an oxygen ion has a charge of... Oh, I said the wrong thing for sulfur. I was doing sulfur's charge. No one caught me. Sulfur's charge is 1, 2, 3, 4, 5. Sulfur's valence electrons is 1, 2, 3, 4, 5, 6. The sulfur one was valence electrons. It has 6 valence electrons. The charge of oxygen in the same group, the same column there, would be negative 2. And for the most part, it would be great. I mean, I think the lowest percentage on any question was an 80%. That's awesome. All right, grab your notes then, which you already have open. You're all going to have to help me. I don't exactly remember where we were because I have too many classes. I don't know. I get confused. What was the last thing you wrote down? Yeah, predicting ions.
I love that.
Do we do this?
Just put me on my put me to my
Predicting ionic charge?
Yep.
All right. But you wrote down the charges of the thing. Yeah, you got the charges there. So we got to this point. Good. Okay. So electron configurations for ions, and that's where we're at. Okay. This is actually relatively simple. Okay. You guys know your electron configurations for the most part. So we're going to be quick with this. Is the electron configuration for a phosphorus ion? Oh, actually here. That's the electron configuration for phosphorus, for the phosphorus ion. Okay, for the phosphorus with charge. That's it. And if you look at that electron configuration, if you did not know that it was a phosphorus ion, you just looked at the electron configuration, you would say that's the electron configuration for what? No, because phosphorus ends in 3p4.
Oh.
Actually, 3p3. Yeah, you'd be like, that's argon, right? Talk to your group. Why does a phosphorus ion's electron configuration look like argon? Why? Talk to your group about it. Talk to your table. You need to join another table. Why don't you sit over here? Actually, yeah, sit over here, because there's only two people there. That's even better. Elizabeth, what did your group say? How come? So something to do with the charge. That's what you're saying. It's something to do with the charge. So this group here, they kind of think, well, must be something to do with the charge, why it looks like an argon electron configuration. Anybody else want to help out? What? What about that charge makes it look like an argon atom? It's a -3 charge, which means what? Why is it a -3 charge? What happened to that fat phosphorus atom to give it a -3 charge? Maybe, but that's not what gave it the charge. That's a specific thing. Come on, guys. Why do things have charges in the first place?
Energy?
What?
Energy?
No. Why? Oh, I'm trying to make. Why do things even have a charge? Why would an atom even have a charge? Because protons and electrons, right? Okay. So why does that phosphorus atom have a -3 charge? Close. It didn't lose electrons. It gained electrons. It gained 3 electrons. Okay. And we're saying a normal phosphorus atom would have 3p3 at the end, right? But if it's an ion, it's 3p6 at the end. There's 3 more electrons. Do you remember the octet rule? Atoms want to be like noble gases, right? They want to be like noble gases, and they will gain or lose electrons to do so. Phosphorus will gain 3 electrons. And then guess what? It's going to look just like argon. If you're only looking at the electrons, it's going to be just like argon. I don't feel like making pilot jokes. Not in the mood. But it's a good one. All right. Nothing. All right. Now, notice the -3 means the phosphorus atom gained those 3 electrons. So wait a minute. Here's one more question. I want a redemption question. I everyone think hard about this, okay? If all atoms gain or lose electrons to look like noble gases, I need your brain in the game. Put it that away, please. I need, if all atoms want to look like noble gases, and they will gain or lose electrons to do that, what is the electron configuration going to look like for any ion?
It's gonna look like 8, right?
Like 8, but that's going to look like what?
It's gonna be like P8, right?
P6, right? Because if you got P6, that means at some point you have an S2, right?
Oh, yeah.
6 plus 2 is 8. If you're going to have an electron configuration for an ion, it's always going to end with P6. It might be a 4p6, it might be a 2p6, it might be a 5p6, but it's always going to end in P6 because that electron gained or lost, that atom gained or lost electrons to look like noble gas. So it's just going to look like a noble gas. Okay? So an electron configuration for an ion is going to look like the nearest noble gas neighbor, always. Try writing an electron configuration for magnesium ion. First, we got to get the charge of magnesium, which you have in your notes. All right. The charge of magnesium plus 2, right? Exactly. Good. Yeah, leave those alone for now. But that's right. We are actually going to do that later. All right. So there's the charge of magnesium is plus 2. All right. Now that means, what does that plus 2 mean in terms of electrons? No, it didn't. You need to reverse your thinking. A plus 2 in terms of electrons means that you lost 2 electrons. You lost 2 negative things. 0 minus negative 2. What's the answer? I'll write it out. 0 minus negative 2 equals 2. Positive 2. That's math. Electrons are negative. You lose 2 electrons, you get a plus 2 charge. And that means you're losing 2 electrons from magnesium, so what noble gas is it going to look like? Yeah, right? Here's magnesium. It's going to lose 2 electrons. It's going to look like neon. Just find its closest noble gas neighbor, and you're going to write the electron configuration for magnesium ion. It's just going to be the same as neon. Notice it ends in 2p6. p6, the end of all ions, electron configuration. And notice that the plus 2 means that 2 electrons have been lost. I am going to post these notes up in the school sheet. Don't worry about it if I speed ahead a little bit. We're a little behind right now, so I'm going to speed ahead. Find a fluorine ion. Do the charge on your own. Do the charge, and then write the electron configuration for it. I'll give you a hint. You know how to find the charge. That's the easy part. You've got a map for that. In terms of writing electron configuration, you really just need to find the closest noble gas to fluorine and write that configuration down. Got something interesting down there? Put that away. Look, guys, it's the same. It's neon again. Why? Right on. Because it gained 1 electron. F negative gains 1 electron, right? Turns into neon, basically. It doesn't actually turn into neon. It just gains an electron, so it has the same number of electrons as neon. Okay? All right. Turn to your partner. Actually, you know what? We've already answered that question. Don't worry about that question. All right. Forming ionic bonds. All right. I want you guys to tell me, you're going to write down all these ions, and you're going to tell me the charge of them. Lithium. Write it down. Write the charge. And by the way, when you write the charge, do this. Lithium is +1. That means it goes in the superscript. Right here. +1. Like that. Superscript. Like Superman flying in the air. Okay? Up high above the lithium. +1. That's how we write the charge. Next one. Potassium. Write it down. Write the charge. Find it on your periodic table. After that, magnesium. Write it down. Find the charge. Write it on your periodic table. After that, calcium. Write it down. Nitrogen. Find the charge. Oxygen. Find the charge. Fluorine. Find the charge. when you're done with that, it shouldn't take too long, right? You got the little map, you know how to do it. It's all it is 1, 2, 3, 1, 2, 3. Positives and negatives, right? Oh, do it backwards. On the periodic table, I'll show you over here. So remember the trick to charges is quite simple, right? You just do the charge is +1, +2, +3, -1, -2, -3. That's it. That's it. We learned that yesterday. Now, in front of you, you and your partner have a bag of ion puzzle pieces to share. Your bag is numbered, I know where that number is, and you have your own colors. If you lose a color and drop it on the floor, I'll know it belongs in your bag, and I will shame you for it. Shame. No, guys, honestly, please be super careful with these. I made these like 2 years ago. I'm not joking when I tell you it took me like 5 hours to cut them. Look at all of them. Look at every single person has one of those. It took forever. Okay, so don't lose them, please. Be careful. All right, pull those puzzle pieces out and check your work. Make sure your charges are right. You just predicted charges. You've got puzzle pieces with charges on them. Find all those things and make sure you're doing your charges right, because that's the most important thing. It might be easy for some of you, but if you're not doing it right, you have to know now, and you have to fix it. So look at the puzzle pieces and see if you're right. You should be right. Hopefully you're right. Find out. So you're trying to see charges. Were you here yesterday? Where are your notes? Pull those out, because you got a map in there to figure out the charges. We'll get there. For now, you're just checking to make sure the charges match what you figured out. Sorry. Well, all you're doing right now, so you were a charge now, right, for all those things? Okay. So, you want to know, are you right about the end? Yes, you are. That's it for now. Are we good, guys? Guys, if you are confused, all you are doing is looking at the charge that's written on the puzzle piece for the corresponding element that you wrote down and making sure that you wrote down the right charge. So you look at the puzzle piece for lithium, you see the puzzle piece says +1, you see that you wrote +1, and you say, aha, I am correct on lithium. Then you move on to potassium, K. Potassium says +1 on the puzzle piece, I wrote down +1, so I am correct. You move to magnesium. Magnesium says +2 on the puzzle piece, I wrote +2. You move to calcium. Calcium says +2 on the puzzle piece, I wrote +2. You move to nitrogen. Nitrogen says -3, I wrote -3. Oxygen says -2, I hope you wrote -2. And fluorine says -1, I hope you wrote -1. All right, so are we good?
No.
Now on to the fun part. We got some more notes to do. All right, notice the charge is written in the superscript. That's important. Whenever you write a charge, an electric charge, right, of an atom, you need to write it in the superscript, up top like Superman. All right. Notice this is underlined. Needs to be in your notes. The formula unit. The formula unit, guys, we got notes to write. The formula unit is the lowest whole number ratio of ions in an ionic compound. And ionic compounds are neutral. The compound itself is neutral, even though it's made out of charged ions. So, we're not going to get there yet. I want to just go over this point a little bit in detail. Because to me, as a student, I would read this sentence and think that, okay, I know what all those words mean, but not quite there on the sentence. That's what I would feel like. In fact, I kind of feel like that now. This is an answer key. It's not, it's just a key, right? If I draw a little black circle, it's a chlorine ion. If I draw a bigger blue circle, it's a sodium ion. And the compound I'm talking about is just sodium chloride, everyday table salt. Okay? First off, here's a compound that you guys are familiar with. What is this?
H2O, water.
Water. And what does this 2 mean? There's 2 hydrogen. The 2 means there are 2 of this thing before it. Okay? And I haven't written anything in the subscripts here. What does that mean? It means there's 1. That means the ratio of sodium to chlorine is 1 to 1. Which means that the ratio of hydrogen and oxygen in water is 2 to 1. Okay? So now, 1 sodium chloride molecule. No, it wouldn't be called a molecule, I'm sorry. It would be called a formula unit. 1 formula unit of sodium chloride would look like that. 1 atom bonded with 1 atom. Okay? But that's not how salt exists in the real world. It's not. You're not going to find, well, I mean, maybe you couldn't find it because it's too small. You're not going to find just 1 atom bonded with 1 atom in terms of salts. What you're going to find is an organized structure. A very organized, beautiful crystal structure. I think I got 1-to-1 ratio, I don't really know. I'm not great at drawing the structure of it all, but what's going to happen? I'll draw one more somewhere. Mine doesn't look very crisp. I'm not very good at drawing. But that's how it's really going to look in nature. Put that away. That's how it's going to look in nature, right? It's going to be a bunch of atoms built on top of each other, right? And if you want to know the ratio of atoms, that's the formula unit. Even though I have 1, 2, 3, 4, 5, 6, 7, 8 sodium ions, I also have 1, 2, 3, 4, 5, 6, 7, 8 chlorine ions. So my ratio is 8 to 8. And you all know that when you have 8 to 8 ratio, you turn that into what? 1 to 1. Just like ratios, you do the same thing like a fraction. Would you ever leave that there?
No.
No, that's ridiculous. You would, of course, you would write 1 over 1. No, you'd write 1. But I'm just trying to prove a point, right? The ratio-wise. All right, let's move on. Good, good, good. That's a formula unit. Puzzle pieces can help determine the formula units for these. We're going to start by using these puzzle pieces. Okay? What I want you to do is I want you to try to make the smallest possible rectangle using potassium and fluorine. Make a rectangle, stick the puzzle pieces together, use the smallest possible rectangle you can do using potassium and fluorine. There it is. And you probably draw something like this.
No, that's a rectangle right here. And then there's another one. And another one.
Right? Is that the smallest possible rectangle?
Yeah.
Or is this the smallest possible rectangle?
The first one.
The first one's the smallest rectangle, because it's smaller. And a rectangle, right? Okay, so what does that mean? What does that tell us? Well, that tells us this. I have 1 potassium for every 1 fluorine ion. Okay? That means this is potassium fluoride. We're going to get to naming it later. What that means is, look, if I want, all right, K plus 1, F minus 1 makes KF. Why don't I write 1s? Because I don't. By convention, A 1, if you don't write anything, it means 1. Okay? A 1 is implied. So there's our first example. All right? The formula unit when K and F bonds is 1 potassium for every 1 fluorine. Okay? And we write the chemical formula like this, KF, which I just did. Notice I underlined something at the bottom there. You're going to want that in your notes. Cations are always written first. The positive ion goes first. A couple of different ways to remember that. It's the second class in a row where someone said KFC. It's just KF.
No, like KFC.
I'm hungry too.
KFC's.
Right on. But that's KFCl. Anyway, doesn't matter. Folks, a couple ways to remember. You have to put the cation first. There is no, if you were, let's say you're talking about table salt, NaCl. You ever heard CaNl? I can't even say it. ClNa? It's not a thing. We don't say it that way. The cation goes first. There's a couple ways to remember that. One, you can remember that cats are the bossiest of all animals, and of course they would go first. Cations go first. Two, you can remember that you're going to just put the thing on the left first. Read the periodic table like a book. Find the thing on the left, write it down. Find the thing on the right, write it down. Cations go first. I'm going to try and trip you up with that later.
All right.
Oh, one more thing underlined. We do not write charges in the chemical formula. It is not, I don't just take the K plus and the F minus and smush them together and say I'm done. I don't write charges. The reason I don't write charges is because ionic compounds are neutral. If I have a neutral compound, I'm not going to put pluses and minuses in it. That's confusing. I'm not doing it. Okay. Here we go. Now I'm trying to do magnesium and fluorine. Did you guys get the puzzle piece made? Should look like that. Right? Magnesium and fluorine put together. So what's the chemical formula then? To show that there are 2 fluorine ions, we put a 2 in the subscript. So it's going to be MgF2. Right? All right, let's do some more. Tell me the formula for magnesium and chlorine. Use the puzzle pieces and then tell me that formula. Why aren't you guys using that? That's the whole point. Work together, put it in the middle. So all right, so we're doing magnesium and chlorine, and it's going to look really similar, right?
It looks the exact same.
It looks the same, but there's a different compound in there. They've got the same charges, so the same thing happens. So magnesium plus 2, chlorine minus 1, you end up with magnesium Cl2. Right? Try oxygen and potassium. And notice that I'm trying to mess you up right now. What am I trying to mess you up with? I gave you the anion first, and you know that you always write the cation first in chemical formulas. So even though I wrote A and K, O and K, you're not going to say it's like, you're not going to say it's K2O. You're going to say it's, wait, you're not, I can't even say it wrong. You're not going to say it's OK2. You're going to say it's K2O, right? Potassium has a +1 charge. Oxygen is a -2 charge. Together, they make K2O. They do start to sound like droid names, don't they?
I got it, but I just think about
All right, this one's kind of hard to make the puzzle pieces. Calcium nitride. I'm sorry, Ca and N. Calcium and nitrogen.
I don't think you can do that.
You can't. You're going to need 2 nitrogens. Stack 2 nitrogens on top of each other. Right? See how that works? So you end up getting something that looks like this. That's my best drawing. See? I don't know what I did. That's right, though. Nope. That's not a rectangle, my friend. What's your other? I can't find. You gotta go. Oh, you can split them up. That's a rectangle. Yep. So when you have calcium, what's the charge? Nitrogen -3. You end up with Ca3N2, right? All right, folks. Ca and O. Easy one, right? All right. All right, you put those together, you can tell that it's got to be. All right.